Hey, John here. Let's look at the Verilog code that we need to use to generate the synchronization signals and some color information so we can generate test patterns like this. A big thanks to everybody that supports my channel and helps me out through the Discord and in comments, likes, subscriptions, everything helps. Thank you very much, especially the VIP patrons listed here. So today I'm going to look at some Verilog code to generate these signals. That comes from this GitHub repo right here. There'll be a link to this below on YouTube in the description of the video. So you can follow along, get your copy of the code. Stuff I'm going to look at today is in this VGA subdirectory right here. We have the synchronization library and a color bar generator application in here. Well, this is where I keep my copy of the code I checked out from GitHub. Get status on my current directory here. I'm good. I'm in sync with the repo. And I want to let's do a make clean up everything. Let's go into the sync directory. This has a simple test app. All I really care about is generating the synchronization signals. And in order to see something on the monitor, I think I turned the screen white or something like that. If we look at the top level file, we see we have a module that takes in a 25 megahertz clock. We bring in the push buttons on the FPGA board, and now that I'm saying this out loud, I've yet to test whether these things are doing anything. It just boots up and starts running, and we'll talk about that in a little bit while. We have 3 single-bit values going out for the red, green, and blue analog signals. They're either full on or full off, okay? So in 3 bits, that gives us a total of 8 colors. We're mostly interested right now in the horizontal and vertical sync signals that go to our monitor. I'm not even going to send anything out to the LEDs on the FPGA module, but that's just in here because I copied the code from some other project. Let's look at the top level here. What do we got going on? Some internal wires that I use to route the output of this VGA sync generator to these signals here, the horizontal vertical sync, and a video active signal that comes out. And what am I going to do? I'm going to send the video active signal directly to the red, green, and blue signals. And these names correlate back to the previous video. I'll put a link to the playlist in the description below on YouTube so you can find prior videos where we talk about the synchronization signals and their timing and how you calculate them and all that. I'm not going to review all that in here. We're going to just dive in and use it. The point is the active video signal is what I'm going to use to just drive these things full on, full off. So whenever there's supposed to be video color information on the screen, you'll see this is true, and I'll make it white. Or we can comment one out and just see that the guns are assigned right. Is the red, and the green is green, and so on. The horizontal and vertical sync are active low pulses. They come out of the sync generator and active high, so I have to invert them on the way out. That's what's going on there. Okay, so everything else is in this VGA sync module, which is right here. So I'm bringing in a 25 megahertz clock. We talked about that last time as well. Now, I have a bunch of parameters in here I have so that I can, in a test bench, I can reach in here and change the dimension of the screen. This is a technique we saw in the previous video as well when we talked about some university notes where somebody set the total number of horizontal pixels to like 5 and so on to make a very tiny synthetic screen so that you could take a step back when you're doing a test bench and see the entire picture without having literally 480,000 pixels worth of data, which is double that many edges, so the application might take a little while to run and to load and to scroll around on your screen. Totally unnecessary if you synthetically reduce the size of your screen. That is why these are all parameters that are able to be overridden when you instantiate this module. You see I did not do that in the top level module we just looked at, so these defaults were all in use, which causes us to have 640 by 480 basic standard, universal basic standard VGA resolution. which works good enough at 25 megahertz. We should be running at 25.175, I believe is the technically correct number. But these days, with non-analog screens and all, I mean, they're incredibly tolerant of all sorts of wacky timing problems and things like that. So this is a perfectly reasonable speed to run at, and it's convenient because we have a 25 megahertz clock on the FPGA board that I'm using to run this code. So what do we got here? Here's the clock, reset, H-Sync, V-Sync, and the video active output signal that we saw when we instantiated it at the top level module. I have local parameters that I use in here to calculate the total number of the counts, how many pixels there are in every row, how many lines there are, or how many rows, we should say, in one screen or one frame, right? Then this includes the front porch sync and blanking rows and columns, okay? We talked about that last time as well. What's going on here? I've calculated at what point does the horizontal sync begin as expressed in pixel clocks. Again, we talked about that last time as well. And you'll see that the origin of the video in this implementation, 0, 0, if this was the screen, is the pixel that's in the upper left corner. So the active video, if we Googled up another diagram here, and we click on images, we're going to have a system that's implemented like this picture here. What are we doing? I'm going to go to the site here. Timing positions, not that. Yes, it'll work like this. 0, 0 is up here, and this is going to be 799 because there's 800 total pixels here. But what is it, 525, give or take this way. So what happens is the rows 0 through 479 are the active rows, and columns 0 through 639 are the active columns. The rest of the time, the video will be blanked, okay? So this one is organized like this. I talked about the optimization of doing it this way last time, and you can see it in the code now, because what happens is the video will be active when the column number in our counter that we're going to use to count the columns as the time passes, the clock signals, the pixel clock free runs for each column starting at 0 up to the 349 or 339. I can't think. 640 by 480 means the columns are 0 through 639, okay? So what will happen in here is if we look around, spoiler alert, there'll be something in here that says if the horizontal sync is less than 639, then the video is active, and it's hiding in here. And it says if the counter is less than the horizontal active video column number, the maximum column, then it should be on, provided that we're on a row that makes sense as well. I'm getting a little ahead here, but you can see that's what all these are being calculated for down here. We got HVID and VVID. So you got HVID and VVID, which are going to be defined up here somewhere. HVID, right? Oh, of course, it is the 640. So you saw the code down there. As long as the column is less than that, it's active. And if the row number is less than VVID, okay? So when both of these counters are less than the 640 and the 480, then we got an active video analog output is running at that time. All right, so we talked about these numbers where they came from different websites around the net last time as well. So what are we doing here? We're going to calculate the 800 and the 5 and change 100 for the number of total rows. We're calculating when the sync signal happens, when it starts and when it ends. Just like the active video, we're going to have an expression down there. You probably just saw it a minute ago, where the if the column, the pixel column, is between begin and end, the H-sync, I should say, begin and H-sync end, then we need to assert the H-sync pulse. At that time, the same thing's true for the vertical sync pulse. which goes on some row number whatever, which is the vertical vid plus the front porch, right? If you go back to this picture here, we got the front porch that's horizontal, vertical. So we're rows, yada, yada, yada. The row number starts at 0 and goes up. And we want to take the active rows plus the front porch rows down here. Let's see if I can zoom in a little bit. Open image here. Right? So however many total displayable active rows plus the number of rows in the front porch equals the first sync pulse line. And the last sync pulse line would be that number plus the number of sync pulses, okay? And that's what's being calculated there. And the end is the same, is the begin plus the number of lines in the pulse. We talked about this a while ago. In order to create a counter that can go from 0 up to HC max, you take the ceiling of log 2 of that number, and that'll be enough bits. So what do we do here? Because we're going from 0 up to that number of bits, we're only going to go to 0 up to that number of bits minus 1. I talked about all this before. To have a dynamically sizable counter that always has the right number of bits, okay, for the columns and the rows. I create a bunch of other registers in here so that I can create a nice finite state machine. These are single bit output values that go on and off when I want to assert the active video, the horizontal sync, and the vertical sync. I mean, that's really all this thing does. It counts clocks and asserts now is a good time to sync and so on out these bits. And then these values, these reg values at the very bottom are assigned to these fields here, video active, H-sync, and V-sync, which are the ports up here, video active, H-sync, V-sync, okay? So that leaves us with the usual state machine. This is generic fluff. We've seen this a million times. Free run. If I'm resetting, 0 everything. If I'm not in reset mode and time goes on, the clock is ticking, I've got a regular finite state machine on the leading edge of this clock. Whatever the next value is that I calculate in the combinational circuit down here, it represents the value that's supposed to be outputted on the next clock pulse, and that's what's going on here. So that leaves us with the combinational circuit down here. And I got a nice note over here that says, by the way, if this should start up, because the reset's really just zeroing everything up here, it might make more sense to choose different values here. So it starts up on a specific row and column that's not in the middle of the active video time. You know what I mean? You can start here. I mean, eventually the monitor will wake up and recognize it. But it doesn't really matter what you do, because when you start up, the monitor is looking for the ability. It's trying to find synchronization signals and measure them to try and determine what format the video is supposed to be in, how many rows, how many columns, how to scale it to fit on the LCD. And now modern monitors, that is, will work that way. So it really doesn't matter where we start. I'm going to start in row 0, column 0 of the active video region in a free run until I get to a horizontal sync, and I'm going to probably waste an entire frame of video, if you think about it. If I was to write the code that runs in the video monitor, for example, which is what I'm getting at here, what does it do, right? I would wait until I got a vertical sync pulse before I did anything. And then I would go from there and look at the horizontal syncs after the vertical sync and try and determine the number of rows and the number of columns based on the time between the horizontal sync pulses, okay? And then I would scale it and put it on my LCD. So my point is, it doesn't matter where we start the video. The monitor will eventually figure it out. So if you want to point out this is starting in a glitchy way, and it might, I don't know if it does. I haven't really given it much thought, again, because it doesn't really matter how it starts, okay? Just that it does somehow. Now, there might be some benefit to not using greater than or equal in here. At some point, maybe we will try to look at how many LUTs it takes to do these operations. It might not take any more to do greater than or equal to versus just exactly equal. Okay? And by that I mean, again, when it starts up, what if there's garbage in the counter? Assuming it could start before without even having a reset signal, for example, right? At which point the counter could have garbage in it. It could be doing weird things and generating really crazy timing, but it would only do it for one wraparound of the counter, which is not going to be very long. It'll be less than one frame time. So again, it probably doesn't matter. And by that I mean I could put exactly equal to this. I put greater than or equal to so that if I don't reset it and the thing comes online with garbage in a counter, and technically it won't do that with an FPGA, it'll come up with 0 because that's how FPGAs are initialized. If I leave them, unspecified in here, they're going to be all zeros. But if you built this into an ASIC, it might have a count value that is bigger than this. And you'd like it to go back to 0 when that's true, is my point. If everything is perfect and it starts at 0, it'll never become greater than, because my code is perfect, right? Point being, when I become equal to the horizontal maximum count value minus 1, I want a horizontal counter to go back to 0, because this value is going to be the 800 that we talked about last time. The HC max is 800. HC max minus 1 is 799. So if the current value, in other words, is 799 or more, then the next value of that counter better be 0, because it should go from 0 to 799, 0 to 799, and so on. If it's not at the end, then advance it forward to the current count plus 1. That's what this is doing. And we're going to see the exact same thing in the vertical, because they both work the same way. But the vertical will only advance when the horizontal counter wraps back around to the beginning. We're counting rows, okay, for the vertical. We're counting columns for the horizontal. A column is one clock tick, one pixel clock tick in width, all right? So what we want to do is we want to say if the next clock tick is 0, what we're really doing is we're asking if this happened and we know we're wrapping the horizontal counter back to 0, then it's time to advance the vertical counter. And we use the same logic here, because the vertical counter, if it goes past the end, it needs to go back to 0, where the end is VC max rows. So if it's greater than or equal to VC max minus 1, right, then make it 0, otherwise go to the next row. And this is the thing that could glitch. This here won't really glitch. If you reset and everything starts up at 0, you're fine and dandy, right? But that also means that this is 0. What does else happen here? Reg is not greater than that, so it won't become 0. This will be set to a 1, because the horizontal counter would also be 0. So actually, when you first power this thing up, if the regs are 0 and the next values are 0, this will immediately become a 1. That won't be true. Therefore, this will happen, and we won't change the vertical counter, which is 0, again, because the FPGA will start that way. You can explicitly start it that way by creating an initial block and assigning these all initial values of 0, again, which is perfectly legal on an FPGA, but not on an ASIC. And actually, this won't glitch, but whatever, I digress. Figure this out, reason it out for yourself, and see if you agree with me on that. My point, though, is whether it glitches or not when it first starts, it won't matter, because once it's running, it'll be fine, and the monitor will still figure it out and do the right thing. So, in quick review here, we get the horizontal pixel counter counts up until it gets to the right side at 800 and comes back. The vertical counter advances if and only if the horizontal counter had just done a wraparound, and it will advance by 1 as long as the current counter reg value is not already at the bottom row. which is not the visible row. It's the row that's way down here after the back porch, right? Because that's what this VC Max includes, the active part, the front porch, the sink, and the back porch. Same with the HC Max up there, right? So as long as we're not off the bottom, we're going to advance it to the next, otherwise we're going to set it back to 0. If we're not at the end of the row, we want to leave it alone, okay? Now, in theory, you wouldn't have to do this assignment, but that would be an inferred latch, right? And you get that warning from the compiler. This is explicitly saying leave the current value in there, right? So how do we know if we are in a video active region, right? Well, if the next value of the horizontal counter is less than the HVID, as I was talking about when we first opened up this module, that little digression, if I'm in the left part of this diagram here, one of these columns, 0 to 639, and I'm in a vertical row that's less than the vertical active video row count. I'm not down here in the front porch, the sink pulse, in the back porch area. In the blanking time, if I'm not in the blanking time, I need to assert the video active signal so that anything using this module knows when to turn the color guns on, okay? And that's true when we are in the right columns and the right rows. Otherwise, it goes 0. And the same kind of logic applies down here for the horizontal sink, the vertical sink. And again, we talked about that at the beginning. If the next value of the horizontal counter is greater than or equal to begin and less than end, then when we get to that particular time period, that next clock tick, we want to assert horizontal sync. Otherwise, we don't. Okay? Same thing with vertical. If the vertical counter is on a row that makes sense, greater than begin and less than end, then we set that one. Well, these signals being routed out after the clock ticks, propagating through our state machine into HSync reg and VSync reg, and then routed out down here to the signals coming out of the port. These go directly to the VGA monitor. So if the vid active, HSync, and VSync signals all are going high and low at the right times, and we just simply hook these things up to the wires going to the VGA monitor, we should get a white screen, or whatever color the top is going to propagate out in these assignments down here. And I assigned it to each one of the 3 outputs, therefore it's going to be white. Okay? That is assuming I get the right resistor sizes in there. We'll talk about that in a minute. So what else do we got? I got a test bench in here that does what we saw last time. We're going to generate, we're going to instantiate, I should say, an instance of the VGA sync module. I'm going to override all those parameters and say I want the screen dimension to be artificially small, so I can take a zoomed out picture of it in my waveform diagrammer, my simulation tool in waveform viewer, so that I can see that it is going on and off at the right times given these values, okay? And all I'm really going to do is send in the clock and the reset signal. I don't care about any of the outputs from the VGA sync module because I can reach inside with the simulation tool and see what the counters are doing anyway. They're not going to be used otherwise for anything else. So what am I going to do? I can do the usual thing here, initialize the clock to 0, open up a dump file so I can plot it. I've got a free running clock. I'm going to reset for a couple of clock ticks. Then I'm going to turn off the reset. I'm going to wait a little while to let the thing run, hopefully long enough to take, this times this plus this plus this and so on, number of rows and columns, and see if I can generate enough data to see a whole screen load of clock edges. What happened there? No VCD. Uh-oh. Oh, no. I logged into my Raspberry Pi and ran this. This is my desktop. What am I going to do here? Get status. Let's log off the Pi for simulation and run it on my desktop. I'm in the same directory on my desktop here. I'll need to do a git pull because I don't think I updated. No, I did not. Git status. Here we go. Make clean. Make plot. There we go. And now we can see this. This is the beauty of having a nice Git repo. I don't ever have to back up anything that's on my Pi because it's in my Git repo. If my Pi goes away, I just start up a new one and do a Git checkout and pull all this stuff out of there. So all I'm going to do is take every signal, throw it on my screen here, and do the usual thing you've seen me do 100 other times. Zoom way out, and voila! We now have so much stuff, it's a little overwhelming. Let's turn on the horizontal wave highlight right there. So when I do this, you can see the row there. Let's shrink this down. Then we can what? I can put it in the background. Sounds like we got some excited dogs in the other room. All right, so I hit Control-Z, for those of you not following too closely here, to put the plot in the background. And now I have a prompt here, so I can say, what? View the VGA sync file here. And that's not what I want to look at. I want to look at the test bench, because I want to see these numbers, okay? I'm going to see if I can get all this on the screen at once. Hey, there we go. All right. So the red signal over here, this guy here, you can see that's reset. He's resetting and then he goes low there. These are all garbage until the first clock edge wakes up in the state machine and it notices that the reset is asserted and it zeroes the counters. Okay, there's the horizontal sync register counter that goes to 0, and the vertical one goes to 0 then as well. All right. So you can look at the next and the current values next to each other, and obviously the next is already moving on to column 1, saying the next one should be 1 because the current one is 0. Next is in the next value that's going to go into the horizontal counter register on the next leading edge. Of course, it doesn't happen here because reset stays on for a little while, so it stays stuck until reset goes off. And then we see a rising edge, at which point the 1 is copied into the horizontal counter register, and then the horizontal next one goes to 2, and so on. So that's a very standard hallmark signature of a counter, okay? So that's what's going on. You see it go from 0 up to D, and then back to 0 again. Now, we configured this in decimals, so what I can do, you can actually do this on multiple rows at once. If I highlight them, I had the control key down. So if I hit 1, I hold on control, I hit all these other ones here. I right mouse and go to data format, go up to decimal because I configured it in decimal. I want to see these in decimal. Here we go. All right. Let's look at the horizontal counter value and the horizontal sync register output bit. Okay, as you can see, this edge here goes true when the count goes from 6 to 7. So what I want to know is that going true at the right time? We also have the video active signal right here. Is that true at the right time? Okay, well, the video active should go true from pixel 0 up to pixel 4, and it's not true yet. This might have to do with the reset signal. Let's look at video active of the second frame. This one, when it's 0, it is true. So this is part of the glitch on the first time. This is wrong. If I really wanted to, I could make it work right. But this is what I'm referring to. When the first time it starts going, this doesn't work. And remember, it makes a little bit of sense as to why. It needs a leading edge in order for it to react to the current value in the H counter next in order to determine whether the video should be active or not. It can't go active earlier because the reset is holding it low here as part of the reset logic in the finite state machine. All right. So again, the first time it's going to be squashed and weird, but once it wraps around, starting here, it should be fine. So let's go ahead and move over to the right here a little bit and look at the second frame rather than the very reset first frame. We could clean that up later if we really want to, but as I explained before, it really doesn't matter because of the way the video monitor works. Video monitors take several frames of video before it determines the synchronization and turns on the screen. Anyway, I mean, almost an entire second, for crying out loud. Honestly, I don't know why it needs more than one frame. What are you going to do? Change it between frame 2 and 3? I mean, I can see it skipping the first one it thinks is passed because of glitchiness, like you just saw. Just about anything could be screwy. You could plug in a cable or something like that, and there could be noise. But once it gets one whole video frame, I would say, fine, throw it away and read the second whole one, and then by the third frame, you should have an image on the screen. Not the 70th frame or whatever it is. I just don't get that. Part of my personal opinion of get moving, and I press a button. If I feel the key move, I need the answer on my screen, kind of thing. What am I waiting for? I don't know. Anyhow, maybe we'll build a video monitor some other day. For now, we got to live with what we got. Okay. Back to reality here. Video active goes active when pixel of the current horizontal counter value, which is the reg value, not the next one, right? So when I'm on pixel 0, you see this thing go active. Video active goes true. What is that? Why do I got video active on here twice? Video active 1, video active. Oh, the reg. This is the video active signal coming out of the module. This is the register that is the thing that holds that value. So yes, these are going to be doubled up. Like I said, a lot of noise on this display. I'm sorry about that, but this is everything, okay? Nothing's hiding here. What do we got? So video active goes true on column 0. It stays true until we finish column 3. So we should then have, that's video active next. I need video active. It's on from 0 to the end of 4, which makes a whole lot more sense because that's a total of 5. 1, 2, 3, 4, 5 clock periods, and that's what we have up here, and that's what it should be, okay? After that, there should be 2 pixel times of front porch, 1, 2. Then we should see the horizontal sync go true, which is right here, and we see it go true for 3 pixel periods, 1, 2, 3 right there, and then it goes back down. Now we're in the back porch. There should be 4 back porch pixels. 1, 2, 3, 4. And then after that horizontal back porch is done, the pixel clock should go back to 0, and we should have active video again, which we see down here. Okay, and we can see the counter going back to 0, and that is the H counter reg value, and not the next value. The current value is 0. Video goes active again. You also see in here that the video, the vertical row number has advanced at that exact same time as this thing moves from the max over to 0. That's when this guy here is supposed to advance. You can see the next thing getting ready and saying the next one shall be 2 on the next leading edge clock that comes by. So you'll see this little leapfrogging going on at the counter, on all these counters, okay? And anything in the state machine kind of has this getting ready, and then the next value is latched into the state latch, okay? And again, we see the video active going on for the, whatever it is, the 5 pixel periods in here. And what do you do? If you pick a row like this and you use the left and right arrows, left arrow, and if I hit it 1, 2, 3, 4, 5, you can use that to count the edges on the signal that you've selected, okay? So that's another way to do this if you want to move that cursor around once you click on the screen and you have that cursor, right? So you've got this, the video goes off, and you're in the front porch for 2, so I can go 1, 2, and now we can see the horizontal sync signal here go up, right? I got to go back here if I want to keep clicking on the edges on this row. Otherwise, it would leap all the way over to there, right? So what do we got? We got horizontal sync on. It's supposed to be for 3. 1, 2, 3. That looks good, just like the other one, and we're off to the races. So if I zoom way out here, what's happening, oops, I got an extra cursors on the screen. Okay, so what do we got here? See the vertical sync here? All right, so let's zoom way out. Now remember, we have a synthetically small screen. We were looking up here at all the horizontal stuff, and that all looked good. What about the vertical stuff? Well, there's the video active. There's the 3 rows. Row 1, row 2, row 3. And you can see that because that's the vertical counter register thing. He holds the row number, 0, 1, 2, and so on. We can see that this thing advances at the right time. I think we already saw that. Whenever the horizontal guy goes from the max value back to 0, we should see this increase. The vertical counter goes from 0 to 1 every time the row wraps around. So that's happening. Okay, now what else do we got? We got a video active for the screen. We looked at that. We got vertical sync. Now, vertical sync should go active, and you can see it happening down here. It's getting ready. The next one and the current one, just like all the other staggered state machine stuff. Which is the absolute hallmark of any Mealy or more state machine is going to have these little leapfrogs going on in them. So the combinational circuit is ready just before the leading edge clock. So what do we got here? Here's the 3 active regions of the rows that we watch. Okay, so the vertical video has 3 active rows. Then it has a single row of front porch, 2 rows with a vertical sync signal asserted, 3 on the back porch. So you can clearly see the active region going active on the 3 rows that are counted off 0, 1, and 2. Okay. 0, 1, 2. It ends here. Okay. Now, the third, which is really the 4th row, which is row number 3, okay, is the 1 front porch row. Now we want to assert the the vertical sync for 2 rows. You can see this thing coming on active, saying the next one should go active on the next leading clock, which it does right here, okay, for the 2 vertical rows, 1, 2. All right, then it should go off, and clearly there's a falling edge there, and it does. Then we should see 3 back porch rows, 1, 2, 3, before you see the next frame begin counting. So let me zoom out one more here. You can see these count out, right? So you got 0, 1, 2 was the active rows, and then you've got the number 3 is the front porch. And then you've got 2 rows of sync, 3 on the back porch, 1, 2, 3, and now you go back to 0 for active row, 0 for your 3 active rows. So this is exactly what you're supposed to see, and this is really great. You know, I say, if you're not following along, zoom in on this thing, figure it out, walk through the code, and this. Through me, this is one of the things that I had trouble with real early on in Verilog. I mean, I knew what it was supposed to do, but it always messes me up with the thing that gets ready early, and then you have it taking place as it propagates through into the latch. This is your leap of understanding here. At least that was mine. So it's the getting ready, and then the latching in is the big leap for finite state machines in general. Okay, I'm just saying. If you're having trouble with it, hop on the Discord or send a note in the chat below to resolve any of your misunderstandings. So if I say make, I'm on my desktop. I got to go back to the my Raspberry Pi in here. Somewhere in here I must have SSH'd into it. There it is, fpga.local is how I get onto my Raspberry Pi. And then we go to fpga. Then what have I got in here? This is all my kind of Verilog examples and my the whole ZAD Nouveau project in here and stuff like that. If you are on the Discord, you hear all about that. Some stuff in here. Okay, so sync. Now, if we just type make in here, there she blows. Now, I haven't really optimized this, and it might have some bad design in here. For example, I don't know why. If you look up in here, it does an analysis of the networks in the design to say that this is going to be a carry chain of an adder in the counters, for example. And it says that there's a lot of LUTs in series, and the fastest that I could ever run this circuit is 79.5 megahertz, give or take. And I only have to run it at 25, so I don't care right now. However, I would hope that I could do better than this. Now, it may be that I told it only needed to run at 12, which is like a default thing. I should set that. I got to look up how to do it. I forgot earlier today when I was playing around with this. But this is pretty important to make sure that that number is always greater than the clock speed you really want to run it at, because it will not work if you exceed this. Okay, and you can load up your circuit with so much junk that it takes so long to do what you're asking it to do between clock pulses that it can't really function at even, say, 25 megahertz. So when you scroll back and you look at the longest path analysis in here, it tells you how it decides, or what's going to happen with all these LUTs that are all in series that takes forever. And would be the thing that limits your clock. So we're good for now. My point there is, if it's not good, we might want to look at how I implemented my state machine in those counters, because there could be a way to do it more quickly that might be run more efficiently, is my point. So I program this on my Pi. Now this is running on my 2057 ICE40HX eval board kit thingy that I designed myself, which is also on GitHub. There'll be links to that as well in the Verilog examples and everything else. Well, here's my white video monitor, which is what it's supposed to do, and here's my 2057 sitting here. If I press this button, it should actually reset it. Button down, button released. That's how long it takes to synchronize my monitor. That works. I'm glad to know about that. What does the other button do? Did I hook up button 2? No, I did not. We just looked at the code. Of course I didn't. So there it is. Now you can see I've got these jumper cables here from these pins on the bottom row. If you look at the PCF file, the first 3 pins on the bottom row that are not ground, this is going to my scope ground obviously, are going to be the RG and B values. Then I skip 2 pins, and this is your horizontal and vertical sync. These wires run around over here to, this is the crappiest breadboard I own. As I touch this thing, the screen glitches and flickers, and you move these little things, I lose sync and everything. You can just, oh, here we go. If I touch it again, the screen will go nuts. Of course, it doesn't do it now that I'm filming, but this is a really bad breadboard, so be careful at if you use a crummy one. You might have to wiggle around it'll parts a little bit. Here you go. Maybe you can see the screen going nuts if I just barely move one of those resistors. So this is one of the cheapo ones. I think I did a video on good versus bad breadboards, and this is one of the crappiest ones, and I know it because there's an X on the end there. This was very handy, and I knew that I was only going to put a couple of parts in here, and I could wiggle them around if I had to, just to test this out. But yeah, get a good one of these things, or you might frustrate yourself. So what do we got here? The RG and B values come out on these wires here, and they go through these three resistors. These are 390 ohm resistors, and the reason I chose 390 is because this particular FPGA, the ICE40HX FPGA that's in there, which I can't do because of the wires are in their way. There it is. Hello, Mr. FPGA. This can only drive 8 milliamps per output pin, and I did not want to exceed the value. So these are 390. You're probably better off with like a 330 or a 360 is probably the right size to get the right amount of voltage on the screen, which is 0.7 volts over here is what you should have if you want white. So my screen, I notice, is a little dark, but that's okay. I don't care. It's white enough. It's a very light gray, and it's doing what it's supposed to do.
and I'm not overtaxing my FPGA. So that is the goal, of course. All right, so these wires over here, these colored ones, they run over there, they wind around the room, and they go into here. I put in, these have these little square ends on them. Let me see if I can find one lying around here. They look like this. Zoom in a little bit. And it turns out that these kind of jobbies fit over the pins of a DB15, not a DB, a D sub 15. Somebody called me out when I called something a DB9, which is really a DE, as in Eddie, DE9 for the RS-232 the other day. But the point is, you know what I'm talking about. It's a D sub connector, the 15-pin high-density jobby, which is what you've got with VGA. These pins are smaller. They're physically smaller than the ones on a DE9, and those little square jobbies that you get with your breadboard kits fit very nicely on the pins in there. If you shove that down on a DE9, it won't really fit, and if you force it, it'll get stuck on there, and it'll kind of destroy the square end on these cables. I'm just saying. So this is how I made my breakout cable. I just shoved them on the appropriate pins. And if you look closely, you can see that red, green, and yellow. I didn't have a blue wire, so the yellow is what the blue is. You can see it. This is the female end with the pins, of course. If you want to do your own and you have if you're dyslexic or whatever. I had to kind of look at this and think about it as I flipped it over from the various drawings. So your RGB values are on the row, that's the wide row, and on the pin end you can see, put them down there on the right. The black one here is in the end of the middle row. On my left end, as I look at it, I would say upside down with the wide end down. That's my ground. And your horizontal and vertical sync are on that top row, the narrow part of the D sub connector. You skip one pin on the left, you put the two in there like that, and then there should be two that you skip over there on the right on that top row. Okay, so that's where all those pins go. I don't remember which is which. I think the orange one in this case is, what is that one? That's the blue one over here. I'll bet that's the horizontal sync. As you can see, the blue wire on this comes out on number 79. We'll go back to the PCF file and verify that that is, in fact, the horizontal sync as it goes through these resistors there. By the way, and I can see in this shot here, those are 100 ohm series resistors for the sync signals. I put 100 ohm in series with these pins just because the FPGA has a very high slew rate of the signals coming out of here, and these wires are all over the place, antennas and long cables, and they're bouncing all over the place, and they're going to get noisy, and they're going to have a lot of overshoot and ringing all over the place. So the idea here is those are just simple TTL signals, and those will dampen the edges on the sync signals using the natural inductance capacitance that is the parasitic inductance and capacitance in this cable so that the signals stay nice and clean. That's why those have those on there. Anything at 75 and 80, 85, even a 50 ohm, 100 ohm, 110 ohm, those are very nominal. Around 100 ohms is what you want to have on there. Do not put resistors that are too small in series with the outputs for the RGB values because you don't want to overload your FPGA, because these wires here inside the video monitor are terminated with 75 ohms inside your display. So the FPGA wants to have at least like about a 400 ohms or more on the outputs, otherwise you draw too much current, all right? So this turns out to be a pretty good size to get the right voltage, which is supposed to not exceed 0.7 volts, by the way, and the analog for the RG and B value should never go over 0.7. That's the maximum brightness signal that's supposed to come out of this wire, which would work fine at around, like I said, 330 ohms in series for this design if we had an FPGA, or maybe you put like an LVC 245 bus driver chip in there to buffer the signal or something to get the current up, you could put a smaller resistor in there. But don't go under 330, okay? So that gives us our white screen. Here's what my scope says is going on right now. You can see a huge amount of overshoot on that top purple trace, which is clipped onto the red video signal. If I move the resistors around on my crappy breadboard here, you can really see that thing glitching around. That's because if I move it and it bounces around, what I'm doing is it's making and breaking contact with the video monitor, and I can see it out of the corner of my eye, and the signal is not being terminated when I do that. So what I'm really doing is, if I pull it out all the way, this is removing the 75 ohm resistor, and the voltage just went up so high it's not even on my scope anymore. So that's why we see that glitchy noise. And here's me moving it around a little bit. That's how great this breadboard is. Don't buy the cheapest breadboards you can find, is the moral of that story. Now, even when it's in, you've got some overshoot, and that's due to the parasitics in the cable, and it's also due to just the messy wiring. These are all too long, and all these cables here are not shielded in any way. This is just terrible transmission circuit. But the beauty is the video doesn't show any, usually what would happen in this situation, if its overshoot is really bad, you'd see a real bright or a weird rolling black haze on the left edge of a brightness transition. And I'm not seeing that on that monitor. So in spite of this outrageously noisy, nasticus signal here, which will probably go away if I etched a board and got rid of all these wires, in spite of all that, the video's looking really good.
So I'm not going to just leave it there. That is enough to celebrate on its own, honestly. That was a great accomplishment. That was one of the first things I did when I got my first FPGA board, which is the Spartan 3E evaluation kit from Digilent. I coded up the same kind of a thing you saw now. Now, I then moved on, of course, to color bars. So let's look and see the difference here, right? So if I say diff, what I did here is I just simply took the vsync in the top file and I copied them over to this new directory called bars, and I made some changes. So what did I change in the vsync.v, or the VGA sync file? I technically didn't have to really change anything, but what I wanted to do is I wanted to make output, make an output port that provides the row and column counter values, the current values, so that the module that instantiates the VGA module can see what the current column and row numbers are. And the value of that is I can ask, hey, if I'm in column 5, turn on red, and things like that. So by getting an eyeball on these, I can do that and draw diagrams on my monitor, which is what we're trying to do here. Now, why are these different down here? HC max equals this. Blah, blah, blah. One more. I think I added some comments or something. Video active. Well, this is just a different tabbing. I should diff it without white space. Diff, blah, 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 minus W that says I don't care if I change the indentation, don't show the line. And it's a little bit cleaner diff. So we got some noise up here. I'll talk about that in a minute. And then we got down here. What's going on? Here's me outputting the row and column numbers. And I have to tell it how many bits wide that port is, and that's why there's noise above here. And I have to assign a value from the counter registers to those ports, the column row ports. So the main thing I wanted to do was add these ports and make these assignments. Okay, and logically, that's all I've done. Now, why is all this other stuff going on in here? Well, what I did is I moved these local params that we saw a minute ago in the sync module, which is still the sync module, but this version of it, okay? I took them out of the local params down here, and I moved them up to the module parameters up here. And the reason I had to do that is because the Verilog does not like it. Let's look at the file. If I use HC bits and VC bits right here, it is very unhappy if they're defined as local parameters way down here. Okay? So they needed to become formal parameters up here so that they're static when the module is instantiated versus later. Honestly, I think this is a little wonky. I don't know why they can't get them from local params, but whatever. I'll get over it. So all I did is move these up here so that they could be defined before I use them. That's all. Otherwise, the only difference is I added these two things, and way down here I said set them to the current counter values. Okay? Now, in the top module, I have made some more changes. I now output the red, green, blue as well. Oh, I did this. This is not changed. Actually, we should do a diff, so I don't get on a sidetrack here. Diff minus W, top V with the one in the sync. In fact, if you do a diff like this and don't tell it what file, it's smart enough to know the same one, okay? So if you're into diffage, here we go. I added these. In the top level module, I have to have a place for the outputs, the column and row counter values to go. And because those are defined inside the module and I don't have access to the parameters, I can't reach in there and steal them. I think there's a way to do that in Verilog, but it's whatever. 9 and 8 are the right values for 640 by 480. And then I have to use you'll see these up here in the module instantiation. And then at the bottom of the top module, you see I have a whole bunch of different ways of generating the red, green, and blue bit values based on the presence of the video active signal and which column and row and all that I'm in. Okay, so this is the only real difference. I made the counter values come out of the VGA sync module, and then I used them in the top module. I use them by assigning them to these wires here, from here in that module, and I got all these variations in here. Right now, what have I got on here? I have draw the same pattern on every row. What do I do? If the video is on, take bits 8 down through 6 from the column counter while the video is active. Otherwise, set them to 0, make them all black. Now this probably depends on your video monitor. You're supposed to blank these things when the video is not active. We talked about that last time. Spec says to do it, you're supposed to do that. Earlier today when I was playing around with this, I forgot to do this, by the way, and the color was okay, but the monitor had garbage all over the screen. Not shocking at all. You violate the rules, you mess it up. So that's why we have to ask if it's supposed to be on, set our red, green, and blue bits, the output bits that we just looked at on the breadboard, to the values of the most significant bits of the column counter. Otherwise, make them black. That's all I'm going to do here. So let's go ahead and program this thingy up.
And there you go. That's what we get to see here, which is pretty cool. So what do we get here? We see black on the left, and that makes a lot of sense, really. Why? Because remember that pixel 0 and row 0, I should say column 0 and row 0, are up here, the far left edge of the displayable area. We know all 3 most significant bits in the counter are 0 over here, so it makes sense that they'd be black. As we move over here, of those 3 most significant bits, we have a 0, 0, and a 1. And they're plugged in, I'll bet, to red, green, and blue. So the blue bit is the only one on right now. And that's when we have an 001 coming out of there, and that makes sense. Then when we add 1 to that and it goes to 2, I have 0, 1, 0. So if they're plugged into red, green, and blue, what happens is the least significant bit of those top 3 goes back to 0, and only the middle bit is on. So that's green, right? And then the next one is 3. Now this is really not white. This is I don't know what color I'd call that, but white is over here, and I think you can see the difference between this and this. This has got some color in it, not quite white, but what this is probably the green and the blue combined. So this is some weird green-blue thing. The next bit is when we have just red, and that's because you got 0, 1, 2, 3, and then 4. So what we're really doing is transitioning from 0, 1, 1 to 1, 0, 0, which means that if we got red, green, and blue, then you got red on and green, blue off. And this transition right here is we're going from 2 guns on and 1 off to a different gun on and the other 2 off. And that's a nice, clean, vertical line. You can actually see the individual transistors on my screen with my phone zoomed in like this. That's a very clean line. I'm very happy with that. In other words, it's not glitching and stuff. You don't see a weird halo of blue cropping up during the transitioning of these bits. All right? So what's next here? We add 1 to that. So this is going to be red plus blue, which gives you a purpley color. And then we have a red plus green, which gives you yellow. And then you add 1 again, and we get a 7, which is all 3 guns on, which is white. Then you get to 0, which is black, and the pattern starts over with blue. So this is exactly what we would expect to get with a 3-gun, 3-bit, I should say 1 bit per gun output coming out of our FPGA. Totally cool.
So let's look at some of these other patterns. This is a really simple one. We're just taking the most significant bits and changing the column value based on those bits changing. Now you can play around with this to your heart's content using different bits for different reasons. This is the full screen on white using a different technique. This is the original version we just saw before. I change it to a concatenated 3-bit value, and if the VGA vid is on, I want 3 bits all set to that. Otherwise I want 0. This is your first step towards these more complicated ones. In other words, you don't send them all 3 like this. If you really want to, you can just set all 3 at once like that, is my point. And that's what we did up here, and we put the count value in here. Let's look at this mess up here. This is a great example of a priority encoder, and I'm sure if we look at the compiler output when this runs, it depends how much it optimizes the design, or how good of a job the compiler can actually do, but this is probably going to run a little bit slower due to the way I designed this, which is, I mean, I admit, this is hard to read. I'm an idiot. I shouldn't have done that. Look what we got here. If the VGA vid is on, and I got 2 open parentheses. Let's go back here. I'm in Vim, so if you hit %, it'll show you the matching paren. So this whole thing is in the parentheses here. So if the VGA vid is not on, this colon here is the one you're going to look at, and we put a 0. It's black. Okay? If the VGA vid is on, then we look at what's in these parentheses here, and we answer these questions. If the row number is greater than 300, then take columns 8 through 6, which is what we were just looking at down here. Okay? When the row number is greater than 300, we're on the bottom section of the screen. If we're not in the bottom section of the screen, but the row is bigger than 290, make it black. So that puts 10 black lines just north, just above the bottom 300, which have those color bars we were just looking at. Okay? Now, if we're not even down as far as 290, but we're greater than 200, so we're moving further up north again, then take the VGA column counter bits 5 through 3 and use those 3 bits. And think about that. Those are ticking along more quickly than the more significant bits 8 through 6. So what we should see here are narrower color bars, going much more, cycling over and over again much more quickly, 8 times more quickly, in fact, than these, right? Okay, and then if it's greater than 200. But if it's not greater than 200, and it's on, but it's greater than 190, we want black. And this is going to put a black bar across the top of this section of faster changing color bars. Now, if it's not greater than 190, just take the least significant 2 bits of the counter. These are going to be changing very quickly. This is going to let us see how big one individual pixel width is on our screen. So in the top part of our screen, every single pixel will have a different color. It'll cycle through all 8 colors over and over and over again for every single one of the 640 pixels up there. Okay? That's what this one's going to do. Woo. This is the pattern I just described, and you can see these going really fast here. Now, this particular video monitor can go a higher resolution, so you can actually see multiple individual, active matrix LCD. There's actually like 2 or 3 LEDs in there lighting up per pixel, because this can do 1024 by 768 native. So in 640, you would expect to see 2 pixels on there actually per column, and you can see the black, blue, green, and so on. That's the 1 pixel per column. Here's the other one that's doing it in, I don't know how many per column there. I'd have to go back and check which bit numbers we're going to use. And then down here we see the fat color bars. And we do know that the fat ones are 8 times bigger than the ones up here. So, and that works out because you see this line up here. There's a 1, 2, 3, 4, 5, 6, 7, 8. And then you go back to black while this one moves on to green. I don't think this is 8-to-1 up here. Oh, it does look like it could be. You'd have to go back and look at the code. Maybe it is. It's just a coincidence. I just took some bits. It is 8-to-1, 8-to-1, 8-to-1. Each one of those. That's a coincidence. That's pretty cool. I meant to do that, right? So anyway, there you have the color bars based on the horizontal and vertical pixel counts and the row counts and all that fun stuff, a la Verilog. So next time we'll have to play around and do some more fancier stuff. So yeah, there's your solid screen, vertical bars, and then groups of vertical bars. You can play around with these count values and write all the if-then-elses to your heart's content and create all kinds of patterns in here if you want. Next time we'll try and put some memory in here, and we'll calculate maybe a text font or something, to a tiled screen or something like that, so they can see what's going on. Maybe we'll take another look at the timing information. This was just compiled. What happened? You'll notice it goes down to 72.3 megahertz. The last build, it was at 79. So that's probably due to the giant priority encoder I put in here. These are not efficient, okay? There's could be other ways to do this, is my point. That could be more efficient. I just slapped this together because I knew it would go, and it's good enough for a demo. All right? So thanks for watching. I'll see you next time.